Hello everyone, it's me Nissan Paudel and welcome to my channel. In this video I am going to introduce you to calculus of variation and also derive Euler-Lagrange equation, which will turn out to be very useful while learning Lagrangian formulation. So without any delay, let's get to the point. But before that, please do subscribe to my channel and like the video. So let's go. Calculus of variation and Euler-Lagrange equation. This might be a new topic for a lot of you, so let me give some pretext first. While doing calculus, we were studying the rate of changes inside a function up until now. Suppose y equals to ax square plus bx be a function. Then what we were doing is calculating the rate of changes with respect to x inside a function, that is 2ax plus bx. In this, we were just calculating the derivative or rate of change of any function yx. But what we will do now is expand this concept to a functional, which is just the value of the function as a whole, which the value can be defined by the user or worker or just by the scholar. So let us define y as ux in this graph. Okay, x as y as ux and another y as ux plus epsilon vx, ux plus epsilon vx. We can also consider it to be hx or anything like that. So what we will do in calculus of variation is study the changes in the y equals to ux as a whole. Okay, so let me define a functional by ju of this function, that is it carries the value for this function as a whole from a to b, suppose. Okay, and j u plus epsilon v will carry the value from a to b, and consider this c2. Okay, I can consider it a to b as well. We will now study the rate of changes between these two functions. So how we will do it? Let's say we define this functional as a length of this curve from a to b. How can we define it? We know from our previous experience and knowledge that from a to b, arc length is given by root under 1 plus u dot square dx. We will consider this function and generalized it beyond the arc length only. It can take any values, which we will consider to be L Lagrangian. It's just defined right now. It is a function of u in other cases. In this specific cases, it's only a function of u dot, but in other cases, it might be a function of u dot, and x. Basically, we are generalizing it. U dot and x, then dx. It defines this functional ju as some value carried by a function ux from a to b. Now another value will be carried by j u plus epsilon v from a to b as l u plus epsilon v comma u plus epsilon v dot comma x dx. Now while deriving a Euler-Lagrange equation, we are interested in finding the extreme points. As in calculus, if we have extreme points, we can find maxima and minima, right? Similarly, we can find maxima and minima for these functions. For example, this defines the length of arc. It might be anything else. If we go deeper, we can find it for action. So it's a very important result. So we are trying to calculate the extreme points, which will be critical in various places. So before doing that, let us consider Ju itself to be a extreme point. That is, for any function u plus epsilon v, when epsilon equals to 0, it is an extreme point. So what we can do now is dz u plus epsilon v divided by d epsilon will be a to b l u plus epsilon v, epsilon equals to 0, u plus epsilon v dot comma x dx for epsilon equals to 0 will be 0 at extreme points. But first I want to add something here, that u plus epsilon v can define any functions from a to b. Suppose from a to b it can define any functions for, if this can be written as ux and this as vx, it will give some other value hx. For any arbitrary function hx with arbitrary number epsilon, you can get any path to get to from a from to get to b from a. So we can write u plus epsilon v as a general function from a to b, which we'll use here in the later course. At extreme point, the rate of change of this functional, we consider it to be at u, it will be 0, whereas at other points it won't be 0. So sorry, dl by d epsilon as a whole. Okay, so let's get to another page and continue with our calculation. As from a to b, we can write dl by d epsilon as dl by du d du by d epsilon plus dl by du dot by d epsilon plus dl by dx by d epsilon dx. It's a very common thing to do. And here we consider u as u plus epsilon v, as if we have considered epsilon v as del u, right? So we'll write du by d epsilon as only v because it's the only term containing epsilon, and similarly du dot by d epsilon as vu dot, and simply write u dot v dot. And similarly x, since x does not contain any term involving epsilon, it's simply 0 dx. Let me just show you. U dot equals to u dot plus epsilon v dot, and du dot by d epsilon equals to simply v dot. So we have the term dl by du v plus v dot can be written as dv by dx, dl by du dot dx. Now let's remember a very important result. If we write dl by du dot by dx can be expanded as dv by dx dl by du dot plus v d by dx dl by du dot. So we will replace this or this by terms involving these two terms. Okay, so from a to b, dl by duv plus we can write this second term as d by dx v dl by du dot. Our main aim is to bring v and take common, so minus v d by dx dl by du dot and dx as a whole. We can simply integrate this term and get v dl by du dot outside from a to b plus integration from a to b dl by duv minus v d by dx dl by du dot dx. Since in this curve from a to b change in change v is simply 0 because these two curves combine with each other at this point, because at endpoints u has the same value as u plus del u. So we can assure that to be true and write 0 instead, and then continue without second term and take v as common dl by du dot v dx. We are working at the extreme points, right? We are working at the extreme point, so the functional derivative of the functional as a whole du plus epsilon v by dx at epsilon equals to 0 must be 0 for this uh, to be should be 0, so this value must be 0. Here v is an arbitrary function and dx is just a small change in length. So for this function, for this derivative to be 0, this term as a whole should be 0. So dl by du minus d by dx dl by du dot equals to 0. Some people write it as dl by du minus d by dx dl by dp, considering u dot to be p. U dot equals to p equals to u dot equals to du by dx to be 0. So at the extreme value of the functional, dl by du minus d by dx dl by dp equals to 0, and this is known as Euler-Lagrange equation. So this is the video. So I hope you enjoyed the video. So do like and subscribe to my channel if you enjoyed it. Bye bye.